Alrighty, y'all, welcome back to Cruise Kids Online. Today we're gonna have some fun, and again, like always, make sure you write down, or at least make sure to remember any questions you have about the video. Initial thoughts, afterthoughts, and comments. We always want to build and get better, right? So today, again, I'm going to be using a pointer, so try and follow along with that. I will be highlighting some important stuff with that, and we'll see what we can do. Alright, so our title for the lesson today is Around and Around and Around We Go. You can say around as many times as you want, because you're always going to end up at the same place. Hint, hint. So we're looking at an investigation into and around circles. Alright, we'll have some fun with those today. And let's see what you think. Alright, so the last few days we've been talking about angles and congruent angles, so let's take a minute and review just for a second here. We talked a lot about vertical angles, corresponding angles, alternate angles, and same side interior angles. Alright, so here we have this figure that should be familiar to you. We have two parallel lines here. Alright, now again we denote those with these double arrows here, and this is our transversal T. Alright, so just going over these sets of angles again, we have our vertical angles here, which is our beta and betas, and our thetas and thetas as well, okay? And then corresponding angles, remember we said that it was like if we picked up this angle right here and just overset it on this one here, the angles that lined up together or corresponded would also be congruent, okay? Then we look at our alternate angles, and when we said alternate angles, we had a couple alternate theorems, right? To start with, alternate pertain to this transversal here, and then we had exterior and interior, right? So the alternate exterior was this beta here and this beta here, and again, since they're labeled the same, we know that they're congruent, just a fact of the figure here. And then we also had alternate interior, again they're congruent, opposite sides of the transversal inside the parallel line. And then we had same side angles as well, so the same sides sum to 180. Alright, so again, angles are everywhere, so if we just go ahead and move on here, we're going to change the pace a little bit, and of course by pace I mean the shape. So today, like we said, we're looking at circles, and we're looking at angles in the circles, alright? We have more than just intersections between lines and angles. We're also going to talk about degrees on a circle, so keep an eye out for that. Just a little bit of warning. There's not a whole lot of words on the page, so listen closely, alright? So if we spin these kind of things here, we can get all sorts of fun circles. Alright, so let's start with what you already know about circles. Alright, the diameter of a circle is the line from a point on the circle to another point on the circle that includes the center. That means the center is already on the line, okay? The radius then is half the diameter, sure, but it's the distance from the center of the circle to a point on the circle. And when we say on the circle, we mean the line that is the circle, not the shape in it, alright? The circle itself is just the line, it's not any space in there. The circumference then is the distance all the way around the circle. And we can find that using the special number called pi, right? And pi is that really long number that nobody really knows how long it goes, except we know it goes on forever, right? So what I want you to do is write down a quick definition of pi, how you define pi. Yeah, we use it in the calculation of circumference, but what really is it and where did it come from? Alright, so take a couple seconds and do that. Alright, so let's just start with some basic notation and definitions. And I know this isn't very exciting, and I know I tried to stress how informal I want you guys to be and just think and be creative. But this is just some things that we're going to be reading and writing, and it's just going to be easier and faster if we get this out of the way. Alright, so when we're talking about a specific circle, we denote it with just the symbol of a circle, and this is normally just a line with a dot in the middle of it. Alright, so this would say circle B has a radius of 7 feet. It's a real quick sentence, just as an example. And then we're also going to be talking about the arc, and we'll go into what an arc is here in a minute. But this is how we signify an arc. Instead of just like a line where we put a line over it, we go ahead and put an arc. So find the length of arc AB is how that would be read. So a few definitions here off the bat. And this is again just a formal definition which will help us out in the long run. A circle is a boundary that consists of all points that are equidistant from a point. That means if we took a point right here in the center of the circle and we took all the points that are equidistant. That would give us our radius. So if we took a line here straight out and went all the way around and just spun the line, that would give us this circle here. Alright, and then the arc is a piece of the circle. So that's just like from here to here, and we'll have some better examples of it later on in the slides. But just so you have what's going on, alright? Then we'll go back here and take a look at it. And we also want to go over arc length. Here's the formula for arc length, and this is just how you find it if you have your radius in an angle. But we won't be looking so much as how long it is, as to what the degree of it is, and then if we need to, we can figure out how long it is, alright? So the measure of the distance of an arc. So if we went from here to here, we could say, well, that's 10 feet if the radius is 10 feet and the angle is such, right? Alright. So with that all the cool information we have, we'll leave it be for a minute, and this is just a better picture of what an arc is. I pretty much just took and separated this out and said this is 30 degrees. So it'd be like 1/12 of a circle, roughly, right? And that's just a rough example. It's not exact. Don't measure it out. It's probably not 1/12. But we're going to talk more about the degree measure of an arc instead of its actual length, right? And how much of the circle it takes up and not how long it is. So there's all sorts of theorems that we can do with circles and all sorts of different centers, and that's going to be really exciting and a lot of fun for you guys to work with. But it would be boring for me to just give you the theorems, so I'm just going to give you the tools and you guys can figure them out yourself, right? I know, Mr. Cruz, same stuff, different day. But this is important. I want you guys to be creative and play with it. Mathematics is just something that we use to have fun. And I know some of you might disagree, but try. Circles can be a lot of fun. So let's start with just central angles, inscribed angles, tangents, chords, and cyclic figures. Don't get caught up in too much of the terminology, but some of these words should sound familiar to you, like central. Hopefully you guys know what that root word is. Angles, if we haven't heard that one before, you've had some troubles recently. Tangents sound familiar. Chords, and we're not talking about music so much, but we'll get into that. And then cyclic figures, just like your bicycle, things that go around, right? So here we go. Chords, let's start there. A chord is a line from one point on a circle to another. So right now I have a whole bunch of different chords just drawn on here, right? So let's just start with this one. This is a very prime example of a chord. It goes straight across the circle here, right? From point B on the circle to point C on the circle. And then we have a couple different sections here, and these are also diameters, if you notice. A diameter is just a chord that goes through the center of a circle, right? And then these intersect at a point that's obviously not the center of a circle. And we're going to be going into different kinds of angles. Like we can see vertical angles happening here, and we're going to look into different relationships between this angle and this arc, and then the major arc and minor arc as well. Alright, so if we go and look at this figure here though, I've got a couple chords where they just share a point. If we go and look and draw this line connecting it, if we said this is through the center A, and this would be circle A then for us, we see that we have a different kind of a figure happening already. And we know that a diameter, we have 180 degrees on each side of the circle, right? So that means we can do some kind of fun stuff with things only pertaining to that semicircle. Moving on, we're going to go into tangents a little bit. And just like chords are lines in a circle, tangents are almost the complete opposite. And they only touch the circle at one point. So that means it can't go anywhere inside the circle, but it means it shares only one point of the circle. So if you were to graph this line here and this circle here, they would share the same point at one spot in the equation. For one x, they would share the same y. And I'm sorry, again, I moved a little bit ahead there. But then we're also going to look at two tangents and how they interact when they intersect with points on a circle. And then we can look at the relationship between the radius and a tangent and the angles kind of going on here. I'm giving you a little bit of hint, and I might have stretched it a little bit too far. It might be a little bit obvious for some of you guys. But I've drawn another tangent here, and we can see that these angles kind of formed a square. So I want you guys to be thinking about what that can mean for these angles and this angle here in particular, corresponding to this one, alright? So let's figure out some new stuff with shapes. As like I said, we've seen a triangle on a circle already, and we just saw that square, right? So with lines we can form shapes, and that's a really cool thing. It's really important in circles. A cyclic figure is one whose all vertices lie on the circle. Right? So we have A, B, C, and D are all on this circle here. And I've drawn this dotted line here for you guys just as a little hint that maybe there's some relationship between B and D. And if we can use what we know about quadrilaterals to discover it, bring it with you in class and let's have some fun tomorrow, alright? And I've also got this triangle here, right? And it looks like it's just an isosceles triangle. And just imagine that this point is on the circle as well as this one. This one looks like it's doing alright. But what we see is we have a triangle here, and we're going to say this is a diameter. And then if we have a triangle, of course, we can have a square too, right? We can go and complete that. So maybe that'll give you a little bit more of a hint on what's going on with these two angles, alright? Now don't worry about it too much. But I want you to try and play around with it. Play with some of the numbers. If this is an angle, what does that mean for the rest of them? Think about the implications of what you choose. Alright. Moving on, central angles now. A central angle, if you couldn't guess from the base word of this word, is center. That means at the center of a circle. So these two chords here, known as diameters because they go through the center, include the center as this vertex here, okay? And then they go out to points on the circle. And these central angles, they have a relationship between this arc and this angle here. So if you can kind of use some logic, you can figure, well, if this is 30 degrees, what does that mean this has to be? Because 30 degrees would just have to be 30 degrees out of 360, right? And we know there are 360 degrees in a circle. So have some fun with that and see what you can figure out. An inscribed angle now, notice it's very much not in the center, is just that very different from a central angle. An angle whose angle vertex is inside the circle with endpoints of the chord laying on the side. Alright, so again we have two chords, they intersect at this point, and then we have these vertical angles again, but now we have two different size arcs. They're very obviously different. And what kind of relationship do you think we could find with those? Again, you can play with some numbers, and we also have these two arcs here. So what's the relationship between these four arcs and this one angle? We'll have some fun with that, so be prepared to do some origami maybe tomorrow. And then I just have a brain teaser here for you. Think about a DVD. We have two circles. One is smaller. We have this inside circle here, these two edges, this inside circle where I have this sun located, and this larger circle on the outside where I have this other sun here, okay? So they both complete a cycle. They both spin once around at the same amount of time, right? This one completes a circle at the same time this one does. Does that mean that the outside of the disc moves faster than the inside? Because it's clearly a much larger circle, right? So it has farther to go in the same amount of time. Does that make sense? And so they have to move at different speeds. But aren't they connected still? These are the same two things, right? So how can they move at different speeds if they're connected by a straight line and the distance never varies? So do they move at the same speed? But we just said that this one has to go a lot farther in the same amount of time. So to say it's going at the same speed doesn't sound correct. So think about that and see what you can come up with. You can Google if you want. It's a little involved, but it's still fun with circles, alright? So what is left for you to do aside from just playing with circles? I'm trying to discover some of the relationships between angles, arcs, and line segments in a circle. And then look up a couple theorems online. And what I want you to do is just be able to describe one of the theorems. And then we'll work on proving it in class tomorrow. And we'll have some fun with that, alright? Thank you for putting up with me tonight. I apologize that my voice is a little scratchy. Again, I'm kind of recovering. So come prepared with a good attitude, a couple pieces of paper, a pencil, a ruler, a compass, and a smile, because that's half an arc, right? Thank you very much. We'll see you tomorrow.